Thank you for coming to look at our video on our latest RSC Mechanochemistry paper entitled Modeling Mechanochemistry, Pressure Dependence of Diels-Alder Cycloaddition Reaction Kinetics. The paper is based on transition state theory, where the rate is proportional to the equilibrium constant between the initial state and the transition state. And we can calculate that from the Gibbs free energy change for 1 mole of the reactants from this equation. And the molar Gibbs free energy depends on the internal energy and the entropy, but also some perturbation, for example, of pressure. That then allows you to calculate the way in which the equilibrium constant depends on pressure, and it depends on this volume change. Evans-Polanyi argued that you could extend this analysis using the concept that the rate depending on the equilibrium between the initial state and the transition state using an analogous equation that then predicts that the rate constant depends on the pressure according to this equation. This is known as the Bell model in chemistry, and the delta V dagger is the activation volume. This implies then that the activation barrier for a reaction varies linearly with the pressure, with the proportionality constant being the activation volume. So we use this concept to analyze the mechanochemical rate of a Diels-Alder cycloaddition reaction of 2 cyclopentadiene molecules as indicated over here in the top. We used a method that had been developed previously by Bo Chen, one of the collaborators on this paper, using the extreme pressure polarizable continuum model. So the solvent is modeled by a continuum, and the reacting ensemble is enclosed in a van der Waals cocoon, and the pressure is imposed, or the pressure is exerted by compressing and the reacting system. And this allows you to calculate an energy profile as a function of pressure, and you can see as the pressure goes to 10 gigapascals, then you get a lowering in the activation barrier that tends to 0. Because this is a thermodynamic model, we only need to calculate the properties of the initial and transition state. And we do this for the cyclopentadiene dimerization reaction because we have extensive data on measuring that rate as a function of pressure. So we can use the XP-PCM model to calculate the Gibbs free energy as a function of the volume of the cavity. We can get the pressure from the gradient of those curves so that we can then calculate for the initial and transition state the change in Gibbs free energy, from which we can get the rate constant and find that the agreement between experiment and theory is very good. This assumes that the initial state and transition state structures don't depend on the pressure, whereas in fact, because they are compliant and have some force constants that control the structure, you expect to have the activation length to change with pressure. We can calculate this using the Hessians for the transition state and the initial state for this reaction and get a pressure dependent correction to the energy, which we can show plotted here, where the difference is really very small. So in summary, we can use Evans-Polanyi perturbation method to calculate precise reactions to Diels-Alder reactions, just using the transition state and initial state structures. Higher order effects, at least up to about 3.3 gigapascals, don't distort the values. The Bell model works very well, and in fact in the paper we show that this gives reasonable agreement with a wide range of Diels-Alder reactions. Thank you for looking at our work.